So we'll just proceed with the with another example with a different instance. Now this is like more of a common occurrence when it comes to design of such walls. I'm going to adopt the same procedure where I have modeled a similar building on SketchUp for easy understanding. Before we do that, I want to show you the question first. Let's just go through the question. Yeah, so this is the question. Let me just share the screen. So this is the question. It says that design an interior wall of two-storied building with an RCC slab of effective span 2.65 meter. The wall is 3.6 meter long and it is stiffened at ends by 100 mm thick intersecting walls, as shown in the figure below. The ceiling height of each floor is 3 meters. With reference to the above diagram, above figure, the wall AB is to be designed. We need to design AB, which you can see in the diagram. Let the thickness of the wall be equal to 100 mm for calculating self-weight and slenderness ratio. So, just like in the previous problem, we are to assume a certain things over here. For instance, the thickness of the wall is something that is fundamental to be assumed. So as a standard, we will always start with 100 mm assumption, because you can't go below 100 mm as a minimum. 100 mm is the least you can assume for masonry walls. So assuming the thickness as 100 mm, let's just proceed further. The basic compressive stress of masonry is 0.96. Over here, he has directly given the basic compressive stress. You need not calculate based on the mortar grade, based on the compressive strength at the end of 28 days offered by masonry unit. You need not check the table 8 or you need not check the table 1 and table 8 over here. It's a direct value which is 0.96 Newton per mm square. Next, the wall AB is supporting a slab with width of 2.65 meter. Now, let me just show you the model, how this looks like. Please switch off your microphones. Okay, now let's get back to the screen share. Now, if you see this particular, this is your previous problem. Where you have the structure with just one single masonry wall, and it is a two-storied masonry wall. This problem is about having intersecting walls at the ends. You have two intersecting walls on either end of the masonry wall, and of course I have just kept some reference with live load, a small figurine which is over there, which is nothing but live load. And this is the wall which we ought to design in this problem, and these are the end conditions as in the supports, the lateral supports. If you can recall, we had something called calculation of effective dimensions, that is effective length, effective height, effective thickness. So effective height is all about the support conditions, that is the restraint conditions of the top and bottom support, that is roof slab and the bottom floor. These are the two restraint conditions we consider in order to calculate the effective height. But for effective length, we check for the end conditions, and we check for the conditions that are in lateral direction, that are supporting in lateral direction. Let me just show you the IS code over here. This is your, excuse me, not this, where is your IS code? Yeah. So in your code book, if you just scroll down to effective length of the wall, table 5, the effective length of the wall, you have different conditions over here. If the wall is continuous and supported by a cross wall, it is 0.8 times its length. If the wall is supported by a cross wall at one end and continues with a cross wall at the other end, it is 0.9 times L. Similarly, if the wall is supported at each end by a cross wall, it is 1 times L. I think condition number 3 is something that comes into picture for this particular problem. So it is table 5 that we ought to refer over here. You should be really careful about choosing what kind of tables you're going. I mean, what are the tables that you ought to look for when it comes to a particular problem. Since we have lateral conditions and lateral support systems that are involved over here, we will have to check for table 5, that is effective length. In the previous problem, in the yesterday's problem, we didn't have any end lateral conditions. We didn't have anything that is supporting in lateral direction. That is why there's some background noise. Please mute your mics, please. Please mute your mics. Guys, you'll have to mute your mics, please. Munib, please mute your mic. Right. So, yeah, in the previous problem, we have seen that there is no lateral supports or lateral end conditions that is happening in the example 1. But in this example, you have end conditions which are two cross walls that are on the either side of the wall which we have to design. If you can see, I have shaded differently for the two types of walls. This is the wall that is stiffened by the help of the cross walls on the either side of the main wall. Now, let's just walk through the design procedure first. It is more or less similar to that of your previous problem. Let me just take you back to the example. Yeah. So the design problem involves, the design procedure involves the simple calculation of weights, just like in your DRCS, your design of reinforced concrete. It's the same thing. You calculate your self weight by multiplying it with its total volume. You multiply its density to its total volume to get the mass. And similarly, you add everything up, the live load, the dead load. You add everything up to get a complete lump sum load. I'm not going through this again because this has been repeatedly delivered. I don't think it is necessary for this short session. So I'll just walk you through though. Over here you can see the load from the roof. The load from the roof slab is equal to 1 into 1 into 0.1 into 25, which is 1 into 1 into 0.1 is nothing but the volume in unit volume, and 25 is the mass, is the density or the unit weight, which will give you the total load that is happening from the roof slab. Similarly, weight of 80 mm lime terrace. When they say lime terrace, it is about the topmost slab which is happening on the structure. So even for that, the weight is 1 into 1 into etc., which gives you 1.96. And lastly, the live load, the small figurine which is represented in the SketchUp, that is the live load, which is of 1.5 kilonewton per meter square. A total of 5.96 kilonewton per meter square is the load happening from the roof slab. Again, this is purely the load happening from the roof slab. If you see over here, that 5.96 is only happening by the virtue of these two. The highlighted elements in this model is the load of the roof slab. This includes the weight of the slab, which is gray in color over here, and the weight of the 80 mm thick terrace, that is in cream color over here. So now that we calculated the load of the roof slab and the live load that is happening on top of it, now we have to calculate the load happening on the first floor or the lower slab. Now for that, again, it's the same logic. We are finding the weight of 100 mm slab plus floor finish plus live load. In the same similar manner, we get a 4.7 kilonewton per meter square. Next, self weight of the wall. Now that we have who is shady here? Right, please mute your microphones. Who is shady? Any idea who is shady? Okay, shady's out. Right. Guys, can you all hear me? Am I clear? Hello? Okay, it's fluent, no? There is no interruption even in the model. The model is visible. Is the model visible? Right. I'll just proceed. Now, if you look back into the question, again we have the self weight of the wall, which is nothing but length, thickness, height into the number of walls into the density of brick wall. Again, we have gone through this yesterday. I'll just walk you through again. Now, the self weight of the wall is nothing but the weight of the wall which you ought to calculate. That is the middle wall, the wall which is stiffened. This wall is what we ought to calculate for its self weight. So the self weight of this wall is nothing but its volume into its brick, unit weight of its brick, in order to get the total weight of that particular wall. Now, once you have that self weight of the wall, since you have two walls, one above and one below, you're just going to multiply into 2, since there are two walls over there, and you get a total weight. Coming back to question, you get the total weight of 40.25 kilonewtons. Again, over here, the total load on the wall total load on the masonry wall is the total load happening on the terrace plus total load happening on the first floor plus the self weight of the wall. Now, 2.65, if you recall, 2.65 is the width factor. I mean, the factor by which you will have to, it's not a factor, it's basically the width of the slab which is resting on top of it. For instance, if you come back to the model, 2.65 is nothing but this length. The length which is over here, this is 2.65. Okay, I just annotated that is 2.65. Now, the entire weight should be transmitted to the wall, so that's why we are multiplying with its width factor. Moving on. Now, once you multiply it and you add the total self weight, you get 40.25 kilonewton per meter as the total load happening on the wall. Now, let's calculate the effective length of the wall first. Now, when I say effective length of the wall here, yes, you should not be confused over here, because the usage of the word effective is slightly ambiguous. Because one thing is, effective length of the wall in terms of masonry structures is nothing but something that is coming out of table 5. Okay, let me just show you that as well. Table 5, yeah. Table 5 shows the effective length of the wall. That is nothing but purely dependent upon its end conditions. If you have supports on either end, it is 1L. If you don't have something, so it's completely dependent upon the condition of the support. But when it comes to the actual length, I think the better word to prefer over here is actual length, because effective length means it's purely codal specific. You can just replace effective length of the wall with actual length, which shows that 3.6 meter plus 2 into 100 by 2, that is giving 3.7 meter. I'll just try to show you in picture what that means. So when it comes to the actual length, we know that the clear length of the wall is 3.6 meter. This is purely from the question. The clear length of the wall is 3.6 meter. The inner wall to inner wall distance is 3.6 meter. Now, in order to get the actual length of the wall, you will have to do the center to center distance of the end conditions. That is the cross wall which is happening over here, which is of 100 mm thick, and the center of 100 mm is nothing but 50 mm. Again, another cross wall which is happening on the other end, which is 100 mm thick, and the center to center distance would be away at 50 mm. So that is what that calculation meant, 3.6 meter plus 100 by 2, which gives 3.7 meter. So if you ask why are we doing the center to center process, I mean why are we calculating the center to center length instead of going for the clear end to end length, is because if you can recall in your design of RC structures, you have in IS 456 there is a clause, I think it's something around I think it's clause 22, let me just check, clause 22, I'll just share that as well. IS 456 clause 22, yeah, effective span, yeah, 22.2 in IS 456 clause 22.2. if you see, for a simply supported beam or slab, the effective span of the member is not, if that is not built integrally with its supports, shall be taken as clear span plus the effective depth of the slab, or beam or the center to center of the supports. Okay, it says center to center of the supports, whichever is less basically. So we are trying to take the center to center of the supports because ultimately that will be less in most of the scenarios, and the same analogy is applied in this particular problem as well. If you see the model, we are trying to take the center to center distance of the end supports in order to get the actual length. Okay, again, just be a little careful with the word effective length and actual length. You need to know the phenomenon why of what we are trying to measure over here. Don't confuse with table 5's effective length and IS 456 effective length. We need the center to center distance, and that is the distance, center to center distance, that we have to consider for calculating the effective length from your table, I mean table 5 from IS 1905. That is this one. Just a second, where is IS 1905? Yeah. So after you get the center to center length, we are going to apply table 5 in order to get the effective length of the wall. A little check, I just want to check everybody is understanding. I just unmuted all. Can you all hear me? You're able to see the codes, you're able to see my references, you're able to see the model. Okay, back to the class. Okay, I'm muting, I'm getting back to the class again. Guys, please mute your microphones, don't unmute them again. Yeah. So now let's just proceed back to our problem here. Problem, where is that? Yeah. So if you can see, that is the reason why they have multiplied 3.6 plus 2 into 100 by 2, which gives 3.7 meter. That is the center to center distance of the wall we ought to design. Now, moving on, since the wall is supported at ends by cross wall, its effective length is the same as its actual length. Table 5 for reference. Let me just take you to table 5. Yeah, in table 5, if you see condition 3, where the wall is supported at each end by a cross wall. Okay, now it's the same condition which we have in the model. Both the sides of the wall which we have to design is supported by a cross wall, and if that is the case, it is just the length multiplied with 1. It's just the same. The length will remain the same, 1 times its actual length. So let me just show you that in the model. In the model, since there is cross wall on either end, one here and one here, it is that condition 3 where the effective length of the wall which is in between is nothing but its actual length multiplied to 1. So it will be the same 3.7 meter. Same thing will apply for the lower level as well. Now, moving on. Yeah. Since the wall, finish that. The intersecting of the wall can be assumed equivalent to piers of dimensions as shown in Fig B, center to center. Spacing of piers is 3.7 3.7 meter. Width of the pier of direction is okay. Now, if you see the model, let me just show you the model here. I'll just move the slab a little bit aside so that it will be clear from a top view. Let's move him as well. So if you see the plan view of this, we know that the thickness of the cross wall, which is given in the question as 100 mm, this one, okay, 0.1 meter, and we know that we assume the thickness of the wall which we have to design, that is the stiffened wall, is assumed as also a 100 mm thick wall. Now a thing about this is, if you see, this is more or less similar to the setting of a pier. Of course, these two are the cross walls which are happening on the either end, but it can be looked in a way that these are actually piers. Now, what is a pier actually is that, let me just show you in the same wall representation. Now this is a pier. This is how a pier looks like. This happens on the either end. From it happens on this side of the wall and that side of the wall. If it's not a complete wall, if it's not like a complete wall, if it's like a broken, if it's like only a short column kind of a wall, we can say it works like a pier. So when it comes to piers, there's a small clause in your code that says that. Let me just take you back to the code. Yeah. In your code, if you go to, just a second, that will be somewhere in between table 6. Yeah. If you see clause 4.5.3, for solid wall or faced wall stiffened by cross walls, same just as in our case, the appropriate stiffening coefficient may be determined from table 6. Okay, I'll come to that later. On the assumption that the cross walls are equivalent to piers of width. Now we are trying to assume the cross wall as a pier over here. We're just trying to convert a cross wall into a pier, into a pier kind of a formation. Now for that, the width of that particular converted pier is equal to the thickness of the cross wall, and the thickness equal to 3 times the thickness of the stiffened wall. Okay, now let me just share the entire screen over here so that it will be easy for you to just a second. Let me just put this side by side. Okay, so if you're seeing for a solid wall stiffened by a cross wall. Now when they say a solid wall stiffened by the cross wall, this is your solid wall which is over here. Just a second. This is your solid wall and it is stiffened by the cross walls. Okay. It is assumed that the cross walls, that these two cross walls which are in lighter color, are assumed to be act like piers. They are equivalent to that of piers. Piers is nothing but, like I said, it is this kind of a formation. We are just trying to convert an entire cross wall into a pier like a formation for an easy calculation. So when we assume a cross wall as a pier, what we do is that we need to make sure that the dimensions of that pier complies with the clause 4.5.3, which is nothing but the pier's width should be equal to the thickness of the cross wall, and the thickness should be equal to 3 times the thickness of the stiffened wall. That is the width of the pier. For instance, if you come here, the width of the pier, that is this distance, should be equal to the thickness of the cross wall, but I'll just put it on a much more easier diagram over here. It's there. Yeah. So the width of the pier, this is your center main wall. This is your cross wall's thickness. The width of the cross wall thickness should be equal to the main wall's thickness, but the thickness of the pier should be 3 times the thickness of the stiffened wall. As you can see, it's clearly depicted in this diagram. 3 times TW. TW is nothing but the thickness of the main wall, and TP is nothing but the thickness of the pier. Same way, if you're trying to look in this particular perspective, this will be 3 times the thickness of the pier, and this will be equivalent to the, I'll just put that over here. Let me just put 0.10 meter. So that is over here. Yeah. And this should be 300 mm. Let me just pull that to this point. Yeah. So as you can see, the thickness of the pier over here is 100 mm, and this is 300 mm. The thickness of the the width of the pier is equal to the thickness of the main wall, and the thickness of the pier is equal to 3 times the thickness of the main wall. That is what that is represented in this hand-drawn diagram as well. So now that you got that logic, let me take you down to the code. Now, once we assume the cross wall to be a pier, then we can go to table 6 in order to get a stiffness coefficient, because stiffness is all about, how can I put this? Let's say, okay, if you are trying to add any sort of lateral supports, if you're trying to add any sort of reinforced, not reinforced as in your steel reinforcement, any sort of supporting reinforcement on the lateral sides, your entire wall is stiffened. I mean, the masonry structure, the entire plate is stiffened. Okay, the best example is your stick file. You have your stick files which you put your assignments in, right? In the stick file, when you remove the stick, the file is, it's highly, it's bendable. I mean, it's flimsy. It's not stiff. It simply bends. You can crumble it. But when you add that stick in order to hold your papers inside the file, it automatically stiffens the entire file. I mean, that is how the file is being stiffened by the virtue of that stick. The same logic applies to your walls as well. When you are adding a separate lateral support systems like a stick over here, it is a pier, it is going to give a certain amount of stiffness to that particular lateral wall. If you see our model over here, in the model, when you're adding these cross walls, now piers, this will impart certain amount of stiffness to this particular wall. In the previous problem, there are no cross walls. So you can say this wall has the tendency to bend, or this wall has the tendency to fail because of having no stiffness element involved over here. But in the same case, if you're having two cross walls on the either end, the wall in the middle, that is the main wall which you have to design, is more stiff. It imparts better resistance to any sort of failure. So if this is the criteria, table 6 will come into picture. Table 6 is all about adding that little stiffness coefficient that is necessary if you are having any sort of lateral supports, and this has to be complied with your clause 4.5.3. That means you will have to convert your cross walls into piers and then refer to table 6. In order to convert the cross walls into piers, the analogy is you will have to make sure that the thickness of the cross wall is 3 times the thickness of the main wall, and the width of the cross wall or the pier is equivalent to the width of the main wall. Next, coming back to our question over here, quick check. I hope you can all hear me. Just give me some feedback. Can you all hear me? Is my screen visible? Can you see my screen shares and everything? Great. Okay, I'll get back to class now. Right. So moving on. Now, once you get the thickness of your pier, the so-called converted pier, which is 300 mm, you need to calculate the ratio which is happening between the total effective length and the thickness. If you remember the effective thickness, we calculate the effective thickness. In order to calculate the effective dimension, we calculate effective length, effective height, and effective thickness. Now, this SP by WP is all about effective thickness. This total effective span by total effective thickness, which is 3.7 meter by 0.1 meter, which gives you 37. That is your slenderness ratio. The idea to calculate all these effective dimensions is to get the slenderness ratio ultimately. So in order to calculate the slenderness ratio, you are multiplying effective height. You're trying to get the ratio between effective height and effective thickness, or effective length and effective thickness. Now it depends. What you have to choose over here is completely dependent upon the particular scenario. So over here it is effective length to effective thickness. You get 37 over there. Now the ratio which is happening between the thickness of the pier and thickness of the main wall is what that is necessary in order to look up for table 6. If you look to table 6, let me just brief you with table 6 here. There's something called stiffness coefficient, and the stiffness coefficient is dependent upon the ratio between the thickness of the pier, that is TP, and thickness of the wall, that is TW. Now if TP by TW is 1, 2, 3 or more, you have appropriate stiffness coefficients that you will have to multiply to your actual results. So in order to calculate that, you will have to find the appropriate value that is coinciding to the appropriate stiffness coefficient and the slenderness ratio, which is the slenderness ratio over here in our problem is 37 and the stiffness coefficient ratio is 3. So if you come back here, the slenderness ratio 37, which is greater than 20, so we'll just consider the last row over here, and the stiffness coefficient is 3, so we'll be considering the last column over here, that is 1. You have 1 as a stiffness coefficient which is happening for that particular criteria. Now the stiffness coefficient is 1. Now the effective thickness, the entire point of all these calculations looking up to table 6, making sure that they are complying to the certain clauses 4.3 etc., is in order to calculate the effective thickness. The effective thickness will be equal to the stiffness coefficient which is obtained from table 6 multiplied to its total thickness, the total thickness as in the actual thickness of that particular wall, which is nothing but 100 mm over here. So 1 times 100 mm, that is 100 mm, is what is shown in the example. Next, let's calculate the effective height. Till here it's all about effective length and effective thickness. Now let's calculate effective height. Effective height, since it's a fully restrained setting, the effective height, just like your previous problem, it is 0.75 times the actual height. So 0.7 into 3 meters, which is 2.25 meters. Again, the slenderness ratio based on height. Previously, this is the slenderness ratio based on length. This is the slenderness ratio based on height. Again, effective height by effective thickness, that will give 22.5. And we are going to consider the slenderness ratio in the heights perspective, because the load is happening from above, it's happening vertically downwards. The possibility of failure is also in vertical direction. The failure might be bending, it will bend. It's not happening in lateral direction, it's happening in vertical direction. The bend or the failure will be happening in vertical direction. So in such a that is the reason why we calculate the slenderness ratio based on height over here, in order to get our basic compressive strength and permissible compressive stresses. Now, for a slenderness ratio of 22.5 and zero eccentricity is what we have considered over here. We go to table 9. Let me just take you to table 9. Just a second, I need to update a little thing, a small thing. Guys, if the connection cuts down, actually, please rejoin again. Okay, I'll be sharing the class again. Please rejoin, because it's a 40-minute session, so it might be disconnected in between. So make sure you rejoin. Right. So coming back to your table. Yeah. So in table 9, just like in previous problem, we have our stress reduction factor, which is based on the eccentricity and thickness of the wall. Since we have considered the eccentricity as 0, anything divided by 0 will be 0. So we will be taking the stress reduction factor in the column happening in 0. I think Anamika had this doubt in the previous session, in the last class which we had in the college. You had this doubt, how are we multiplying, how are we looking for an eccentricity of 0? We have a column of 0. Apparently we didn't look at that particular column. We were just focusing on the other columns which are happening over there. So we ought to look in the 0 column. In the 0 column, for whatever slenderness ratio which we have got in our particular effective height to effective thickness ratio, we will be taking that stress reduction factor. So if you see over here, the stress reduction, the slenderness ratio is 22.5, and at 0 eccentricity you get 0 by 22.5, that is 0. Now you can linearly interpolate and get that stress reduction factor. There, linear interpolation is possible, which is given in note 1 below the table 9. So once you linearly interpolate, I'm just walking you through, there's no calculation possibility over here. So the stress reduction factor is 0.55. Just make sure that you see the correction in red. It's not 0.455, it is 0.55. Moving on, the permissible stress. Ultimately, we need to get the total allowable stress that is happening on a column. So the permissible stress is nothing but all the factors which we find multiplied to its basic compressive stress. The basic compressive stress which you get from table 5, if you recall, table 8, the basic compressive stresses. Now, from that basic compressive stress, which is already given in question as 0.96, if you see the question as it's given as 0.96 over here, 0.96 Newton per mm square. We are just going to multiply this stress reduction factor 0.55 to 0.96. That will give you a factor of 0.53. Please mind the correction. This is the correction over here, not 0.437, it is 0.53 Newton per mm square. Next, permissible load is okay. Now this is the permissible stress. Now permissible load, you are just going to multiply with its thickness and its unit length. Once you do that, you get 43.7 kilonewton per meter is the permissible load, and the actual load which has happened previously, it is 40.25 kilonewton meter, and the allowable load is 43.7 kilometer. So it's a safe assumption. Your wall that is assumed as a 100 mm thick wall, your 100 mm thick wall which you assumed over here, will be able to withstand the load of 43.7 kilonewton per meter. But the actual load happening by the virtue of the live load, by the virtue of its self weight, is just 40.25 kilonewton per meter. Again, it's not a mandate that you have to stick to a 100 wall. You can increase the thickness of the wall. It is advised to increase the thickness of the wall because there might be other unpredicted loads that might cause some sort of failures. There might be some loads that there might be some errors in construction as well. So you want to consider a slightly thicker wall more than 100 in order to safely withstand the load. So this will conclude your example 2, which is a different scenario compared to your previous example. This is when the ends are supported by cross walls. We will have 2 more examples, preferably example 3 and 4. We'll go through this in the next session, but for now we'll just conclude this session because I think 40 minutes are up. Now I'm going to unmute all of you just to know if you have any ambiguities and doubts regarding in this regard. So anybody has any doubt? So is it absolutely clear? You understood the entire design logic? Okay. Nonetheless, the video is already recorded. This video will also be shared just for a second reference. If you miss, maybe you can start again from the beginning. So with this, I'll conclude the class, assuming that nobody has any doubts. I will see you again on Friday. I think we have a session on Friday, maybe. Yes, it's already there upon Edge. You can just log into Edge and download it from the resources. All these problems are shared on Edge. No, we are all following just one Edge. Whatever section 1 is following, the Edge platform for section 1, we are following the same thing. Section 2. Okay, so you can, everybody is, all the Masonry elective students will be on one Edge platform. There are no 2 platforms here. It's just for avoiding confusion. So it's just one Edge. You can just log in and download the copies over there. And even the links for today's session will be uploaded on Edge, and also it will be shared on WhatsApp as well. Yeah, I mean, there's still some ambiguity in terms of evaluation, but then make sure you have a soft copy of it so that we might ask you to send it either by email or because some of you are having problem in uploading the documents to Edge. So if that's not the case, we might ask you to share them through mail and we might evaluate by digital means. So it should be either Knuckles sir or me. Sorry? That we are not, I mean, we don't have any clear information on that. That is completely a vague assumption. Let's just hope it doesn't. No, okay. Let's just assume that the Bandh is not going to extend. Let's just assume that the lockdown is going to end on April 14th, and let's just proceed with that work. But as long as the Bandh or the lockdown is happening, you will be having some sort of interaction with faculty in order to it should go. I mean, it's a very difficult thing. Okay, very well. I'll just leave the topic to you. But as far as your assignments are concerned, we are still having a little discussion in that regard, whether to take it from Edge or whether to ask you to send through email. So make sure you have soft copies of it. Those who already submitted hard copies to me or Knuckles sir back in the college sessions, you need not worry. We will evaluate it somehow. But those who didn't submit yet, make sure you submit it online or make sure you upload it on Edge. Okay. Fine, then I'll conclude today's class. Yes, that's already recorded. It's already recorded. It's already recorded. Okay, there are 32 participants. It's a good turn up. I think only 6 or 8 students are not there today, but that's fine. The session is recorded anyway. We'll try to share it to them as well. Oh, okay then. Thank you, man. Bye. Bye.